To describe the position of an object like a robot in a coordinate system, we are usually using three values, which are the translation along x, the translation along y, and the translation along z. So if you want to move the robot up a little bit, like so, we have a vector 0.3 for x, that is 30 centimeters along the x-axis, 20 centimeters along the y-axis from here to there, and 10 centimeters up the z-axis from the origin of the coordinate system, which is down at the root of this coordinate system shape that I created here. A different way to look at this is to think about these numbers here as coefficients to what we call basis vectors. I have illustrated this here on the whiteboard. And so now you can see that a point is a linear combination of three coefficients, C1, C2, and C3, with basis vectors for the x-axis, a basis vector for the y-axis, and a basis vector for the z-axis. So in this case, the position of this robot here is given by C1 being 0.3 times the x-axis, plus 0.2 times the y-axis, plus 0.1 times the z-axis. Once you work this out, you will find that P just becomes a 3×1 vector, which has exactly these values in it, because these basis vectors are not doing much. Now the point I want to make is though that you can now easily transform this equation into a matrix multiplication, where you have what we call a rotation matrix that is multiplied with a vector of coefficients. And with this, I want to make the point that a point in a coordinate system is really just a point in a coordinate system that is given by three basis vectors and then computed by multiplying the matrix with the vector of position. So if you do this, you will have 1 times C1 plus 0 times C2 plus 0 times 3. In the next row, you will have 0 times C1 plus 1 times C2 plus 0 times C3, and so on. So you will see that this to the right here is actually identical to this notation to the left. What I've also done is writing that down even shorter and saying that a point P in a certain coordinate system is given by a point C transformed, as we say, by a rotation matrix into P. In this case, P and C are identical because we are using the basis vectors from a standard coordinate system.